Hello, excuse me. Welcome to Algebra 1, Lesson 4.1. We're going to get into the vocabulary today of the topics of the lesson. So we're going to just give an overview of what we're about to cover. So let's get to it. I'm going to go ahead and share my screen here. A lot of this vocabulary at the start will be things that we've already gone over in Unit 2 or Unit 3, but stay with us because at the end we will have definitely some new vocabulary for you that you need to make sure you pay attention to, and make sure you're taking notes in your notebook. You should have every vocabulary word written down. You should have a brief description in your own words. Now, if you've written them down in other chapters, you do not need to rewrite them. But you do need to keep a running total of your vocabulary words. I like to have a divided spiral notebook, like a 5-section spiral notebook, and maybe at the first section have just vocabulary words, and I can add to that every chapter. In the second section, I can have my notes. In the third section, I can have my work that I've done, all of my assignments. I can show my work. So maybe even just a 3-subject notebook is good, but any kind of a notebook where you can keep good notes that you can look back on, and it's not loose leaf. So it's not going to get out of order. It's not going to get lost or misplaced. So we're on Unit 4, Lesson 1. And the first vocabulary word that they give us in this unit is the word algebra, which we already went over, but algebra is just the branch of mathematics in which we use letters to fill in for unknown values. The definition of algebra actually means restoration or completion. So we're completing something that's incomplete. It's incomplete when it has a letter in it, and we have to complete it by figuring out what value that letter represents. So that is algebra. Average rate of change. The average rate of change is when you have 2 points on something that's graphed or some data information. It can be in a chart format. It doesn't have to be in a graph format. You have 2 pieces of data, and you want to find the change between them. Usually there's going to be 2 sets of measurement between them, such as a rate of change could be your speed. You've got distance over time, right? Well, also in a graph specifically, like we have here, we're going to have 2 points. And so it's the vertical change over the horizontal change, or the rise over the run. And y'all should be very familiar with this, but you can see that we don't always have a constant rate of change in this graph. There is not a constant rate of change. What we've found here is the average rate of change between these 2 points. That's saying on average, if we took every single point and found the difference between all 2 points, every set of points on here, the average of them all is 0.5. Continuous. A continuous function is a function you can draw without lifting up your pencil from the paper. It never stops. So this would be a continuous function, and it continues on forever and ever, right? So then our next one is a discrete. These are not connected. Sometimes it's a set of points, such as this. Sometimes it can be 2 separate rays. Remember, a ray has an end point and then continues on forever and ever in in one direction. So in this graph, we have a point, a ray that starts here and continues to the left forever, and then one that starts at the same point but continues to the upper right forever and ever. So those could also be discrete. Domain. So domain are all the possible x values of a function, or the inputs. A better way to put it would be the input values of a function. So a graph or a given set of ordered pairs. Yeah, right there it says the input of the function. So if you have 2x plus 3 equals y, whatever you can input to x, in this case it would be all real numbers. So whatever you can put into y for the domain, any numbers you can put in. So if you had something like 3 times 1 over x plus 2 equals y. You would now have a limit on the domain because there is something that x cannot be. Remember, we can never have 0 as a denominator in the domain. So the domain for x in this case would be x is not equal to 0, but x is all real numbers and other than that, right? So domain is going to be all possible inputs for the domain. Range. It's a set of possible outputs for a function, a set of all possible y values. So again, if we had 2x plus 3 equals y, it's this y right here. It's dependent on what x is, what our input value is, determines what our output value is going to be. And that's our range. So when you had a linear function, if we had a horizontal line, for example, the domain was all real numbers, but the range is going to be, let's say this is 0.03. So the range in this case would just be 3. It doesn't go above 3 and it doesn't go below 3. So the range is just the output value or the y values. All right, so an ordered pair. An ordered pair is a set of numbers that indicates the position on the Cartesian plane, or one of the, where you graph things is what you know it as, right? The all of a sudden I can't remember the other name for it, but what a point is. So if we had this point here of 2, 3, this is our x value, this is our y value, meaning this is our horizontal movement and this is our vertical movement. So we've moved over 2 places to the right and 1, 2, 3 places up vertically in order to find 0.23. And so this right here is what we call an ordered pair. An ordered pair will always be inside of parentheses, have a comma separating it, start with the horizontal value, and then end with the vertical value. If you're looking at a graph of speed versus time, then this would be the time function, and this would, or amount, and this would be the speed amount. So it's not necessarily always x and y, but it is always horizontal and vertical. And usually that relates to x and y. All right, end behaviors, what a graph continues to do as it exits from your page. So if you had an array that, let's say, was graphed like that, we could say that its right moving end behavior is to positive infinity, right? If you had a line that went both ways, both its right and left. Let's do it down here. Right is to positive infinity and left is to negative infinity, the left end behavior. So the end behavior is what's happening to the graph when you can't see it. An irrational number, all right? And this is a number with a decimal that never terminates, which means ends, or repeats. So a lot of times irrational numbers are going to look like square roots. The square root of 2, the square root of 6, the square root of 7. The square root of 9 is not irrational because you know that the square root of 9, if you simplify that, if you do the math, becomes simply 3. And 3 has a decimal that ends. It ends right here before the decimal place, right? Because if you were to keep going there, it's just zeros after that. So that is not considered an irrational number if you have a square root that you can find an answer to. Some other irrational numbers are things like pi or Euclid's number, things like that. So you will have a number with a decimal that never terminates or ends is considered irrational. Natural numbers are numbers that we call counting numbers. So if you have a bunch of items and you start counting them, you're going to start at 1, and then you're going to count 2, and then you're going to count 3, etc., etc. So these are all the natural numbers. So you go up by a single integer continuously to infinity, starting with 1. Whole numbers are all of the natural numbers, but we start at 0 this time. So 0, 1, 2, 3, etc. Real numbers, real numbers are any number that's either rational or irrational. Both of them together constitute all of our real numbers. So I don't think we've gotten to rational yet. That must be the next slide. But rational and irrational numbers. So basically every number except imaginary numbers. And who remembers what an imaginary number is? We talked on it very briefly, but an imaginary number is the number I, which stands for the square root of -1, because you cannot have the square root of a negative number because any two numbers multiplied together will always be positive. So it's impossible to have a square root of a negative number. So that is imaginary. Any number that's not imaginary is a real number. We also have complex numbers, which is a combination of real and irrational, such as 2i. So the number 2 mixed with an I. Coefficient. You know what? It didn't go over rational numbers, so I just real quick want to go over what a rational number is. A rational number is any number that can be expressed as a fraction, which also means, I prefer the decimal definition of it, which means that it has a decimal that ends, which means terminates, or repeats. So if you have a decimal that ends, that's like 0.25. Now that can be expressed as a fraction, such as 1/4. If you have a number that repeats, such as 0.3 repeating, that's the fraction 1/3. Okay, so a decimal that ends or repeats is a rational number. Whole numbers like the number 743 are also rational because they have a decimal that ends. Their decimal ends before it even gets started, right? You can also have mixed numbers like 2.5. That is a rational number because that's the same thing as 2.5, a decimal that ends. So those are rational numbers. All right, a coefficient is the number just before a variable term. So if you have something like 2x, the number 2 before the variable, x is the variable, the letter is the variable, the number 2 before that, this is the coefficient. A variable, this is the letter that holds the place of a missing number. So going back to 2x, the x is our variable. Expression. It's an incomplete math sentence, meaning there's no equal sign. So when I was writing 2x before, that's a type of expression. Now, if I were to go on and say 2x equals 7, then this is now an equation because it has an equal sign. This is an expression. This is an expression. And then all together, the whole thing is an equation. Okay, so we've got two expressions that make up an equation. There's an expression on the right side and an expression on the left side joined together by an equal sign. That's what makes an equation. All right, an exponential function. This to me, I think, is the first new vocabulary term that I wanted to go over with you. This is a nonlinear function. And its independent value, meaning its variable right here, is going to be an exponent. So far we've looked at things like 2x or 5y minus 3x equals 2. So we've used a lot of variables that are right here just sitting on the line, right? But aren't in this superscript format, meaning as an exponent, right? And so when we have an exponential function, you have the variable as the exponent. So sometimes this is up here in my definition, I have y equals a to the power of x. Some people write it as y equals a times b to the power of x. Those end up being the same things. It doesn't really change too much, but I just want you to be familiar with both ways that it's written. I also want to go ahead and show you some exponential functions. So I'm going to get out of this and go here to Desmos, the graphing calculator online. So what I have graphed for us here in blue is a picture of an exponential function. Now, if you've ever heard of anything, say, that's increasing exponentially, this is what it would look like if you were to graph it. Some things that increase exponentially could be your interest that you gain in a checking or savings account. Checking accounts usually don't have interest these days, but a savings account, a money market account. Also, the fees that you pay on a credit card can increase exponentially because they charge interest rates if you carry a balance, right? So these are ways that it can increase exponentially. Also, it can decrease exponentially. In the red here, I have shown you some ways of things that decrease exponentially. When you're testing an item in science, say you have a fossil and you want to see how old it is, there's a particular thing that you can test for and how it has, what its unit of measure is now will tell you how old it is because it decreases exponentially. And so this is a graph. The red is a graph where it decreases exponentially. If you notice, that means that we have a fraction or a decimal as our base number with our exponent being our input variable, right? Or independent variable. Whereas our blue graph is a whole number too. Half is the same thing as, or the opposite of 2 because it's 1 over 2. It's the inverse, right? So we have here the graph of 2 in blue, 2 to the power of x, and the graph of the inverse of that, the inverse graph. And as you notice, they're just mirror images of each other that flip over this vertical axis right here, the y-axis. They've just flipped over that. And so you can easily see that. And that actually brings us to our next slide here, horizontal translation. A horizontal translation is a shift in a figure on the coordinate plane. That's that word I couldn't think of earlier, the coordinate plane that moves horizontally. So we have got a graph. Say we have a graph like this. And if it's going to move horizontally, it may end up looking something like this instead, or this. So it just changes places horizontally by scooting to the right or to the left. That's a horizontal translation. It can happen with anything that you've graphed. If you have a straight line and you have a horizontal translation, it just is going to move directly to the right or the left. And you will have that same line with a horizontal translation. So a translation is when we've moved something on a graph. Horizontal means right to left, okay? So we've got a reflection. That's what we were just doing on Desmos. When we've got a reflection, it's a mirror image being flipped over something. So we started with a graph that looked like that, and then we moved to a graph that looks like that. Well, those were, and I didn't do a very good job. So actually, let me go ahead and get back out of here and take you back to Desmos. So we've got these two mirror images, but we can also have mirror images or a reflection over the x-axis. So these two went over the y-axis, but let's look and see what happens over the x-axis. So we've got here, the blue graph is reflected over the x-axis and showing me now the black graph. And you can see that all I did to go between the blue and the black is I changed it from a +2 to a -2. So depending on what numbers you have determines the output of what your graph will look like. So let's see how we reflect the red graph. The red graph is half raised to the power of x. So if I have -½ raised to the power of x, I now have the reflection of that. Now, just a few things about these exponential graphs I want to go over real quick. The only thing that doesn't look like an exponential graph is when you have a base of 1 raised to the power of x. Well, 1 raised to any power is just going to be 1. So that is simply a straight line. So you do need to keep that in mind as well. What happens when we change the base number? If instead of 2, I have 20 or 200, something like that, well, as you increase the number, the slope increases. You see that? The fastness of how quickly it rises goes way up. If you look at this, the curve doesn't begin to start until closer to the y-axis, but it moved a lot faster once it got started. So it took a little bit longer to get started, but once it got started, there was no stopping it. Whereas this blue curve just kind of took its time. It got started early and it kind of took its time. Kind of reminds me of the rabbit versus the tortoise versus the hare, I think is what it's called, right? All right, so back to our vocabulary. So that's reflection and some translations. Interval notation. Now we've gone over this as well. It's a notation representing an interval as a pair of numbers. These numbers are the endpoints of the interval. Parentheses or brackets are used to show whether endpoints are included or excluded. And this is something you should have in your notes right here because it really does a good job of showing us. So if your graph starts at A and is going to the right, A is going to have the bracket, and then it goes to infinity on the right side. Its end behavior is to infinity. And so you have the parentheses there because you can never include parentheses. Now, if you look at one going the other way, let's look at this one at the bottom. This is an open circle. That means A is not included. So in this case, we have a parentheses around A, and it's pointing to -infinity. So we have -infinity here. So this is interval notation. This is set notation. Usually as you continue on into higher education and college, as of right now, college algebra, they prefer the interval notation when noting like domain and range and things like that. So it's good to know. All right, some essential questions we're going to cover in this unit, Unit 4, Module 4. What are the properties of exponents and how do I use them to simplify expressions? What is an exponential function? And how do I graph an exponential function? What are the effects on the graph of replacing f of x with f of x plus k, or k times f of x, or f of k times x, and even f of x plus k for specific values of k, either positive or negative? And how can I find the value of k in the given graphs? What are the key features of an exponential function? And how do I identify them? Why is the concept of a function important? And how do I use function notation to show a variety of situations modeled by functions? What is the average rate of change of an exponential function? All right, so we're going to answer all of these questions in our lessons from Module 4 or Unit 4. So I look forward to exploring these with you and learning alongside you. Algebra 1. See you next.